There is a point of this graph that is behind this vertical line. Where do you think it is? Your natural guess is the result of your intuitive idea of a limit. For more than 2,000 years, people studying mathematics have been concerned with the idea of limit. Much of our progress in mathematics in the past century has been due to correct formulations of this concept. Let's look at some of the ideas behind this formal definition of limit. In an intuitive way, we can find the limit of a function f at a point C by predicting where the graph of f should intersect the line x equals c. The y-coordinate of this point of intersection is the limit L. We consider function values at points on both sides of C converging to C, but we do not consider the function value at C. Thus, the notion of the limit of a function is based on the idea of looking at values of f at points that are close to C, but different from C. The limit is that number which is approximated by function values for numbers that are near C. The neighborhood concept is used to state the more formal definition of limit. If L is a point on a number scale, the set of points less than p units away from L is a neighborhood of L, written n sub p of L. The set of points less than r units away from C is a neighborhood of C. Since the limit does not depend on the function value at C, we will consider neighborhoods with the point C removed. If it is removed from this neighborhood, we use an asterisk and call it a punctured neighborhood. Just as a function f maps a point C onto a point f of C, called the image of C, so too a neighborhood of C is mapped onto a set of points f of n sub r of C, called the image of the neighborhood. In the special case of this reciprocal function, where f of x equals 1 over x, a punctured neighborhood is mapped onto an interval with a point missing, a punctured interval. Given a function f and a point, suppose we decide by using our intuitive ideas that the limit of f at this point is L. To test this guess, we take a neighborhood of L, a target, and try to find a punctured neighborhood of C, let's call it a control, whose image is inside the target. Certainly we can find a control neighborhood whose image is contained in this target, but suppose we are given a smaller target. We can still find a suitable control. A smaller target, a suitable control. Here it appears that no matter what target on L is given, a control can be found whose image is in the target. Thus, L is the limit of f at C. Now, suppose f is a v function, whose tip is above the point C. Let's study the limit of this function at this point. The y-coordinate of the tip seems to be the limit. L is the limit if for any given target on L, we can find a control at C whose image is inside the target. For any given target, a suitable control can be found. So the limit at C is L. Incidentally, we note that in this case, any punctured neighborhood of C is mapped onto an interval without a puncture. If we alter the value at C, the image of a punctured neighborhood at C is not changed. So the limit at C is still L. Here the limit is different from the function value at C. So the function is discontinuous there. If the limit is equal to the function value, we say that the function is continuous at the point. Even if the function is not defined at this point, the limit is still L, but the function is discontinuous. When we look at this jump function, it isn't obvious where its graph should intersect the vertical line at C. So maybe the limit does not exist. Notice how this function maps some punctured neighborhoods onto just a single point. And it maps other neighborhoods onto more complicated sets. L1 cannot be the limit, since this target does not contain all of the image of any control at C. Nor can L2 be the limit for the same reason. Nor can L3 be the limit. If we consider only the part of the function to the left of C, the limit from the left exists. If we consider only the part to the right of C, the limit from the right exists. But since the limit from the right and left are unequal, the limit at C does not exist, and our jump function is discontinuous there. A function may have wide oscillations, like this one. Then the image of a right neighborhood of 0 does not shrink as the neighborhood shrinks, and the limit at 0 does not exist. A function may be unbounded, like our reciprocal function. The images of control neighborhoods of 0 are all infinitely long and can never be inside a finite target, so the limit does not exist at 0. But if the limit does exist for a function at the point C, we can find it as follows. Look at the image of a punctured neighborhood of C and find the smallest closed interval containing the image. Shrinking the punctured neighborhood lets us shrink the closed interval. And when the punctured neighborhood is converged to a point, the closed interval has converged to the limit L. To verify that L is the limit of f at C, we apply the formal definition, which can now be stated as follows. For every target neighborhood of L, there is a punctured neighborhood of C, such that the image of the punctured neighborhood is contained in the target neighborhood. This brief statement embodies one of the most important ideas in mathematics.